Hello, everyone, and welcome to Virtual Planetarium, Exploring Space, part of our MOS at Home programming. My name is Janine, my pronouns are she and her, and I'll be your moderator today. That means I'll be reading some of your questions and responses, which you can submit below using the Q&A button at the bottom of your screen here in the Zoom meeting. If you'd like to see captions during today's program, you can click on the closed caption button at the bottom of your screen and select Show Subtitles. And if you're joining us on Facebook or YouTube, we're so excited to have you here, but unfortunately, I'm unable to see your comments at this time. We're so delighted to have all of you here today as our audience. Let's meet our fearless leader for today's journey.
Thanks, Janine. Hello, everybody. My name is Talia. I use she, her pronouns, and I am going to be your presenter today. So we are starting a new month of programming here for our Exploring Space programs. And the theme for this month is something that we've been calling Weird Math Month. And what that means is that I'm sure it is no surprise to any of you that those of us who make our livings talking about space in the planetarium are complete and total space nerds, because we are. And there are these little aspects, some strange little esoteric aspects about space that we think are just so cool. And we don't usually talk about them in shows because they're concepts that can take a while to explain. And usually we just don't have the time. So that's what we're going to do. And we're going to start with one of my favorite things about space. It's just these very cool things. Now, so when I said, Weird Math Month, if this sort of thing gives you hives, don't worry about it. We're not going to be getting into that. That's not what we mean. We're just going to be talking about these weird things about space. And for me today, it is Lagrange points. So what the heck are Lagrange points? Lagrange points are these interesting places in space. They happen whenever you have a less massive object orbiting a more massive object. So whenever you have that situation, there are these 5 weird points in space around the orbit of the smaller object. And at those places, gravity behaves just a little bit differently than it normally would. And those are the things we call Lagrange points. And I think they're really cool. So that's what we're talking about today. So here is kind of a diagram of what I mean when I say you have these points where you get a less massive object orbiting a more massive object. So this diagram calls the big one mass 1 and the little one mass 2, but that could be, the sun and the Earth. It could be the sun and another planet, or it could be things like the Earth and the moon. Anytime you have a smaller mass orbiting a larger mass. So the ones, of course, we tend to worry about the most are the Earth-Moon Lagrange points and the Sun-Earth Lagrange points. So that's mostly what we're going to be talking about, are the Sun-Earth ones. But there are a couple of other places in the solar system where Lagrange points get very interesting. So that is what these are, where, relatively where those 5 points in space are, those Lagrange points. And this is basically what happens is they move at the same rate as that smaller mass. So if you're talking about the sun and the Earth, all 5, if you put something at those 5 points, they move at the same rate as the Earth around the sun. And you might say, well, of course, why would they not? That wouldn't normally happen in other spots. So let's talk about what I mean. And to help us out, we're going to start with L1, Lagrange point 1, or L1 for short. And again, just to make things a little bit easier to picture, we are going to talk about the Sun-Earth L1 point. So now look at where L1 is. It's closer to the sun than Earth is. It is, in fact, about 1 million miles closer to the sun than Earth is. So think about what would normally happen if you had something, say a spacecraft, orbiting the sun closer than Earth. Think about things that orbit the sun closer than Earth. Would they stay level with the Earth, or would they move at a different rate than the Earth? Go ahead and put your answer in the Q&A. To help, you can think about things like Mercury and Venus, which do orbit the sun closer than the Earth does, and would be sort of a good model for thinking about what would happen if you had a spacecraft orbiting the sun closer than the Earth. So think about it, put your answer in the Q&A. What would normally happen to a spacecraft that you had orbiting the sun at a closer distance than the Earth was?
Riley says it would be a lot hotter.
It would definitely be warmer because it is closer to the sun.
Regina says it's different, but doesn't explain how.
So again, think about, it's kind of easier, it can be easier to think about those planets that are closer to the sun, Mercury and Venus. Do they orbit the sun at the same rate as the Earth? Do they move slower? Do they move faster?
We have an answer from Freya, who says they move faster, and we have one from Jill that says maybe the closer one would go slower.
So the closer you are to this, the closer the planet is to the sun, the faster it orbits. So Earth takes 365 days to orbit the sun. Venus only takes 225 days, and Mercury only takes 88. So they're moving faster than the Earth is because they're closer to the sun. So normally, if you were to take something and put it 1,000,000 miles closer to the sun than the Earth and put it in orbit around the sun, it would move faster than the Earth. It would not stay level with the Earth. It would go shooting on ahead. But not if you happen to stick it at L1. At L1, the pull of gravity from the sun and the pull of gravity from the Earth counteract each other just right, so that if you put a spacecraft there, it stays level with the Earth. It also takes 365 days to orbit the sun. And that's what I mean when I say Lagrange points are weird. They're where gravity behaves just a little bit differently. So what? Why would we care? What would be interesting about a spacecraft that would be at L1? Why might that be a handy thing, a handy place to put a spacecraft? Think about what you would be able to see if you were a spacecraft at L1. And again, one of the major benefits is it's always going to be pretty close to the Earth. But what would you be able to see from L1 that would make you want to put a spacecraft there? Think about where it is and what might be useful to look at from that spot. And again, you can put your answers in the Q&A. Also, if at any point you have no idea what I'm talking about and you're confused and you don't know the answers to these questions, you can always put question marks as your answer, because that is one of the very important things in science, is to know when you don't know something and to be willing to admit it. So think about why you might want to put a spacecraft there at the Earth-Sun L1 point. What would you be able to see that would be handy to see?
All right, we got some answers coming in. Jill says you could see Venus and Mercury, and Julie and Noah say other planets.
You definitely can get views of other planets at some certain points, but there are two things you can always see if you're at L1.
Regina has a good answer, which is maybe both the Earth and the sun at the same time.
Very good. So if you are a spacecraft at L1, depending on what direction you look, you can look to the sun and always see it. There will never be anything in your way. You never have to worry about Earth getting in your way like you would if you were a spacecraft in orbit around the Earth. So you're still close enough that you can talk to Earth easily, which is great, but you don't have anything blocking your view to the sun. So you will always constantly be able to stare at the sun and watch it for things like sunspots or solar flares. So you could constantly look at the sun. On the other hand, if you were facing the other direction, you would always see the daytime side of the Earth. Because you're on the same side of the Earth as the sun, you're just looking at the daytime side of the Earth all the time, which is great if you want to monitor the Earth, which we do. We really like to keep track of what's going on. Weather systems, changes in ice coverage, changes in the amount of land that's forested, things like that are things we always want to be monitoring. So this is a great spot to put spacecraft that look at the sun or spacecraft that look at Earth. And there are spacecraft out there at that point, and that's what they study, such as, I like this one, the Solar and Heliospheric Observatory, aka SOHO, or the Deep Space Climate Observatory, aka Discover, sort of, if you're creative with your spelling. So SOHO stares at the sun, Discover stares at Earth. And that is the perfect spot to put these spacecraft to have that job. So that is one of those weird points. Janine, were there any questions that came in about things I should clarify before we go when we talk about another one of these weird places?
No, just a lot of people being blown away.
Excellent, because I'm about to blow you away a little bit more. So that was L1. Now let's talk about L2. And again, we'll make it the Earth-Sun L2. So once again, this thing is a different distance away from the sun than the Earth is. It's about 1 million miles farther out. And just as a comparison, that is about 4 times as far away from the Earth as the moon is. So about 4 Earth-Moon distances out. And it is farther out from the sun than Earth is. So normally, would something that was farther out from the Earth, would it move faster around the sun than the Earth would, or would it move slower?
And we have a couple people who say maybe it would move slower.
Yeah, think of Mars, for instance. Mars is farther out. It's a lot farther out than the Earth is, and it takes twice as long, roughly, to orbit the sun as the Earth does. So normally something that is in orbit around the sun farther out from the Earth is going to take longer to go around. But once again, not at L2. Something that is at L2 will still take 365 days to orbit the sun, which means it's always going to be close to Earth, but Earth is never going to get in its way. So what kind of spacecraft or telescope or what have you do you think you'd want to put at L2? What might that be a good spot to study from? So think about it. Remember, you can always put question marks if you just really don't know. But what might you want to study from there? Remember, you're farther out. The Earth is between you and the sun.
So we have a couple people who said either the night side of the Earth or the Earth. And Regina says maybe the stars and other galaxies.
Yeah, so again, if you are a spacecraft, a telescope, let's say you're the Hubble Space Telescope, right? That's one of the most famous space telescopes there is. It's in orbit around the Earth, which means, as good as it is, Earth is blocking half of its view at any given time. Earth is in the way of half of the sky. It works around it, but what if you didn't have Earth in the way? You would have absolutely nothing obscuring your view of the rest of the universe. But you're still close enough to Earth to be able to communicate with it easily. So L2 is a great place to put telescopes that are designed to look out on the cosmos. And that's where we're going to be putting, we have right now and are going to be putting some of our next generations of space telescopes. So there right now is the Gaia Telescope. This thing is measuring the positions of billions of stars to such a high degree of accuracy that it's actually allowing us to change what we know about the structure of our own galaxy, even though we're stuck inside of it. Launching later this year, actually just went through one of its final round of pre-flight tests, is the James Webb Space Telescope, often sort of described as being the successor to Hubble. One of the things that's different between it and Hubble is that it's an infrared telescope, and Earth glows in the infrared. Earth is very bright in the infrared. So a great place for an infrared telescope is to be kind of away from the Earth. And so James Webb is going to live out at L2, Lagrange Point 2. And the Nancy Grace Roman Space Telescope is also going to be joining it. I'm not sure if there's a specified launch date for that one yet, but that's going to be another big, huge new eye on space that is going to live out at L2. And those are just a couple of the spacecraft. It's actually a popular parking spot for space telescopes because it's such a great place to view space from without having to worry that your telescope is going to get too far away from Earth. So that's two of these weird, wacky places. Janine, are there any questions I ought to try and answer before moving on?
There's a very interesting question from Claudia that you can tackle if you like to, which is, what time is it in space?
What time is it in space? That is an excellent question. And the answer is that time in space doesn't really work the same way as it does here on Earth, because of course here on Earth, our time is based on the rotation of the Earth. It takes Earth 24 hours to rotate. And so that's how we divide up our time. Of course, in space, things are moving at different rates. So for instance, if you are an astronaut on the space station, you're orbiting the Earth every 90 minutes, which means you're seeing several sunrises and sunsets each day. Or if you're on Mars has almost a 24-hour day. It's about 24 hours and 37 minutes, which means you can't quite use the same way to divide time that we do on Earth. So most astronauts in space use the time of the space agency, the mission control that is in control of their mission. So for the astronauts on the ISS, that's Houston or Moscow time, depending on which part of the ISS you're on. And that is something that we're going to have to figure out before we ever send humans to Mars, how we're going to divide up a Martian day into good units of time, like hours and minutes. All right, so we will keep going because we talked about 2. I told you there are 5 Lagrange points around any given object. So let's talk about L3. This one, can anybody see what the problem would be if we were talking about the Earth and the Sun? Say mass 1 was the Sun and mass 2 was the Earth. Can anybody see a problem with putting a spacecraft at L3? Go ahead and think about that. If mass 1 again was the Sun and mass 2 was the Earth, can anybody think what could be a problem about putting a spacecraft at L3?
Dennis says it would be hard to communicate with Earth, and Jill says the sun would be blocking it.
Exactly. The sun would be constantly in the way. You would never be able to communicate with it, which means the Earth Sun L3 point is kind of useless for us. We don't want to put a spacecraft there. We'll never be able to talk about it. But this is a case where we don't necessarily want to only talk about the Earth-Sun. There is, of course, these Lagrange points exist for every planet in the solar system. And not that long ago, there was an idea to put a spacecraft not at the Earth-Sun L3 point, but at the Earth or the Venus-Sun L3 point. This telescope was going to be called Sentinel, and its whole job was going to be to look for hazardous asteroids. This would actually be a pretty good spot because you could face it out away from the sun. It would orbit the sun at the same rate as Venus, so once every 225 days, And that would give it a pretty good chance to sweep the sky for anything that would be potentially in the way of Earth's orbit, any hazardous asteroids. This spacecraft has not been, it's an idea, it has not been selected for development, but that is a one way that we could use not the Earth-Sun L3 point, but the Venus-Sun L3 point. Because like you guys figured out, putting a spacecraft on the opposite side of the sun from the Earth constantly would be pretty useless. All right, so there's not a lot to talk about with the L3 point. It's, you know, only semi-useful. So that leaves the last two, L4 and L5. And these ones are a little bit different because they're not in that line between mass 1 and mass 2. They are at an angle. So if we're talking again about the Earth and the sun, this is going to be, L4 is going to be 60 degrees in front of Earth as it's going around its orbit, and 60 degrees, L5 is going to be 60 degrees behind. So if you think about the orbit being 360 degrees, then L4 is going to be 1/6 of an orbit ahead, and L5 is going to be 1/6 of an orbit behind. And for the Earth and the sun, that comes out to roughly 100 million miles in front and 100 million miles behind. So that is pretty far away, but not, so it's still relatively close enough that talking to a spacecraft or of some sort that in those places would be relatively easy. So we haven't put any spacecraft at the Earth-Sun L4 or L5 points, but there have been ideas that maybe this would be a good spot to put a space station. If we really wanted to try and live independently of Earth without being, you know, totally cut off from Earth, L4 or L5 might be a good place to put a space station. It's a stable orbit. You're going to always be the same distance away from Earth, so your distance away from Earth isn't going to change. And that is a distance that you can't cover quickly, but you can cover fairly quickly, is decent, you know, as travel times in space go. 100 million miles doesn't take too long, especially if you're got something at L5. It would be relatively easy to launch something from Earth and have it reach L5 fairly quickly. So there is actually a group called the L5 Society. And what they want to do someday is they dream about being able to build a space station that will live at L5. It would be mostly independent of Earth, but not completely. And I personally like that idea. So sci-fi writers really, really like L4 and L5. They appear a lot in science fiction. So the other thing about L4 and L5, just as places in space, is this is where things can get stuck accidentally. Of course, I've been talking about us deliberately putting spacecraft at these L5 points, or at these 5 Lagrange points. But let's say you're an asteroid and you're going through space and you're minding your own business, just drifting along, and you happen to get caught in one of these places, one of these 5 points. Well, that's it, man. You're kind of stuck. You're gonna live there now. And we call these asteroids Trojan asteroids. And Earth has had 1 or 2 Trojan asteroids over time, but there's one planet out there that really, really collects them, and that is Jupiter. So at the L4 and L5 points for Jupiter, the Earth or the Jupiter Sun L4 and L5 points, there is a huge collection of asteroids. So in this diagram, this shows asteroids all over the solar system. There's Jupiter. And 60 degrees behind it are this group of asteroids. 60 degrees in front of it are this group. And you'll notice they're divided up into the Trojans and the Greeks. We call all of these asteroids that live in these L points, L4 and L5 points, Trojans, but Jupiter has so many that they started naming the ones at L5 for Trojan characters from the Battle of Troy, and the ones at L4 for Greek characters at the Battle of Troy. So although these are all collectively called Trojan asteroids, the names are sort of divided up based on where are they in front of Jupiter or behind it. And you can see there's also actually a third group called the Hildas, which is right around Jupiter's L3 point. So Jupiter also has a lot of asteroids stuck at its Lagrange points. And this is great for us because that's a ton of asteroids in a tiny amount of space. So let's say you wanted to send a space mission to study asteroids. This is where you want to send them. And that's what we're going to do. Later this year, launching in October, is a spacecraft called Lucy. And over 12 years, Lucy is going to visit 8 different asteroids. It's going to head out to the Trojan group. And I think it actually at one point is going to transfer from the Trojan group to the Greek group. It's going to study 8 different asteroids. No interplanetary spacecraft we've ever sent out has visited so many different places. And we can do that because there's a ton of asteroids in a small space because they're trapped at the Lagrange points. So we're going to take full advantage of this with the Lucy mission. And I have talked a lot about a very weird topic. So if anybody has any questions they'd like to ask before the program ends, I will do my best to answer them. I hope I have not bored anybody because I think these places in space are really cool. These weird spaces where gravity behaves just a little bit differently.
There is a question from Riley that maybe you can clarify. Is L4 closer to the Earth or is L5 closer to the Earth?
They are the same distance. Whoops. So let's go back to this slide. So they are actually, PowerPoint. They're the same distance away from Earth. They're both, one is just in front of Earth as it's going around the sun, and one is trailing behind Earth as it's going around the sun. So they're both about 100 million miles away from the Earth, but they're about equal distance.
Cosimo would like to know, how did we find these Lagrange points?
Math. It's just, this is why it's a good entrance in our month of weird math. Somebody did the math and was like, whoa, there's going to be places where the gravity is going to be a little bit weird. And everybody was like, okay, well, that's a nice theory. Until they started finding those asteroids in Jupiter's orbit, those Trojan asteroids. And everybody was like, wait, there's this weird group of asteroids leading Jupiter in its orbit. And then there's this weird group of asteroids trailing Jupiter in its orbit. And somebody was like, oh, that guy Lagrange predicted that with his math. He was right. Look at that. So it was first predicted through math, and then we found those asteroids at Jupiter's L4 and L5 points, and that proved it correct.
All right. I think that's all we have time for, unfortunately. Thank you, Talia.
It was really, really fun getting to talk about these things for a change instead of just skipping over them.
I love them. I love the idea of just like floating in space with the Earth, just like hanging out in the same place, watching it spin around.
I love just, the little bit weirdness of gravity.
So good. All right. Well, thank you, Talia.
Bye, everybody. Thank you for indulging me.
And thank you all so much for joining us today. We hope you had fun. I'm very sorry that we couldn't get to all of your good questions. There are a lot of good ones. Maybe you'll be inspired to do some research on your own to try to figure out what those answers are, or maybe you'll tune into a future virtual planetarium program. You can find out what other virtual programs we're offering by following the museum on our social media channels or checking out www.mos.org/mos@home. If you're watching us on YouTube, you can subscribe to our channel, and anytime we get a new video, it'll show right up in your inbox. If you enjoyed today's presentation and would like to support more programming like this, please visit engage.mos.org/welcome to support MOS at home. And thank you to everyone who already has. Well, we hope that you will join us again soon. Bye.